Hello, my name is Seth Mew, and today we're going to be going over atomic and molecular orbitals by using balloons. So first up, you have to prove the Vesper shapes with orbital theory. So basically, let's just say this is an electron cloud, or rather an orbital, right? So with Vesper theory, if we have two of them, then they should become a linear, right? So if I'm just holding two, then it becomes a linear configuration. If I add a third one, this should become trigonal planar. Oh, yeah, okay. So it becomes a trigonal planar, kind of, yeah. And it's a triangle on a plane, like a flat plane. Yeah. All right, here we go. Now we're going to try 4 balloons, right? So now we have 4. It's a tetrahedral, which is basically like a pyramid with a triangle center. Yeah, so 4 is a tetrahedral. If we throw in the 5th one, if we can. Okay, yeah, so as you can see, we basically have a trigonal bipyramidal because we have 1 on the top, 1 on the bottom, and then 3 around the side, forming a plane, kind of, if you can see that. And then if you have the last one, it should just go like this. Then we have the same thing, but 4 on the plane, and 1 on the top, 1 on the bottom still. So it's a an octahedral. Yeah, so that's the Vesper. Yes, next up. Okay, so next up we have hybrid orbitals. So hybrid orbitals are basically what you get when you take orbitals on an atom, or yeah, I guess an atom, and then you basically make them so that they can bond together with other hybrid orbitals. But basically, we're changing the orbitals so that they can bond better. The way they change is, okay, so imagine this is the s orbital, right? And then this is a p orbital, right? So it's a singular p orbital, and this is an s orbital, right? So if we hybridize these, then it will become what we know as an sp orbital, which is basically 2 hybrid orbitals. So how I like to think of it as is that basically you take one of the p orbitals and you let some air out of it and then put the air into this. So imagine the air is going from this into this, right? So I let some air out, right? And then I get some more air in the orange one, right? And I just put the smaller pink on the orange now, and we have what's basically a hybrid orbital, kind of. Yeah. I think the orange is supposed to be a little bit bigger, or the pink is supposed to be a little bit smaller. But yeah, you get the basic idea. The same thing would happen here. We increase this one and then add like a small little thing at the end, right? So like imagine this purple one is also it's the same thing as this small pink one, right? So we have 2 hybrid orbitals. And then if we combine them, basically it would look like this. Oh god. Okay, so when we draw it on paper and stuff, right? When we draw hybrid orbitals coming together, we typically leave out the small ones at the ends because I mean they're there, but they don't really do anything. So we kind of just yeah, and then yeah. So then it just looks like this, right? This is a linear formation. I guess we're done with that. So yeah, and then the you can have sp2 orbitals, which are 3 sets of orbitals, or I guess just 3 orbitals, and then sp3, which is 4 orbitals. One moment. So yeah, this is like what we had earlier, where we have like the big one and the small one, right? And so we have 3 of those right here. And if we combine them, right, then it basically, if you look at the big ones, it makes a trigonal planar, right? And then if we take a 4th one, oh god, it becomes a tetrahedral, except this does not look like a tetrahedral. But I mean, it's actually close enough. Yeah, if you just look at the big ones, oh god, yeah, it's basically a tetrahedral. Yeah, so that's how hybrid orbitals are. And then now we're gonna go over pi bonding and sigma bonding. Okay, so this abomination right here is basically C2H4. what's going on here is the blue, like this one right here, is a hydrogen 1s orbital. And then the yellows are the hybrid orbitals on the carbon. And then the green are the 2p orbitals on the carbon. So when we have C2H4, you can really break it up into two sets of CH2. And then the C's in those two bond together. So as you can see, we have on each side, there's two blue, right? So there's two 1s orbitals from the hydrogen. And those are bonded to the yellow balloons, which represent the hybrid orbitals on the carbon. So we have two of them on this side, two of them on this side, right? And then we also have down the middle, this set of yellow right here, which is also a set of hybrid orbitals bonded together. So currently we have 1, 2, 3 bonds, and then we have this green pair at the top, which is the pi bond, right? So basically, how this works is whenever there's a double bond or a triple bond, there are these things called pi bonds inside them. One of the two bonds in the double bond is a sigma bond, which is the yellow one right here. But the other one is going to end up being a pi bond, which basically uses the leftover p orbitals that didn't get hybridized and bonds those together. So as you can see right here with the tape right in front of my face, this is basically what a p bond kind of looks like. It shouldn't be this low down. It should be kind of above the green. But yeah, that's what ends up kind of basically looking like. And yeah, as you can see, actually, the green goes up to the top and the bottom. So the bottom here actually isn't really being used. Neither of the bottom ones are. But when we draw out things like C2H4 onto paper, we tend to keep them there. Because, I mean, like, they're there, they're just not really doing anything, right? I believe it's like they aren't occupying any, or yeah, like there aren't any electrons being occupied inside the space. Yeah, that's basically what's going on here. So we have, once again, we have 4 hydrogen atoms, and then 3 sigma bonds and 1 pi bond. And then finally, with the last point I want to talk about is if they can rotate, basically. I forget what exactly it's called. I think it's like spinning or something. Basically, spinning is, okay, let's real quick. Let's say we have these 2 orbitals, right? 2 hybrid orbitals, I think really any orbital, and they're bonded together. What can happen is, if it's a single bond, they're allowed to spin, right? So you can rotate them. You can't see this, but like this, so showing around like this. So you can rotate them, right? You're free to do that with a single bond. But when you have a double bond, 1 second. Okay. When you have a double bond, there's one bond in the yellow right here, and there's a bond in the greens right here with the tape. So now if I try to rotate it, it stops because I had to destroy that top pi bond for me to get anywhere, because it's kind of preventing it from rotating. Because if there's only 1 point, then you can rotate all you want. But if there's 2, then like it just won't work, because that's just not how circles work and rotating and stuff. So this cannot rotate. However, one long moment. Okay, so here we have what's basically an H2O2 molecule, which is 2 sets of oxygens. Yeah, so this is supposed to be bonded if I cut the tape. 2 pairs of oxygens with 2 lone pairs, which are the purple. 1 hybrid atom or orbital bonded to a hydrogen, and then another hybrid orbital bonding the 2 oxygens together. So it's a set of those 2. So here, the only bond in between the 2 oxygens is a single bond. So if we wanted to, we could rotate 1 molecule of HO, however we like, along this axis. So we can rotate it all we want because it's only a single bond. But earlier, once again, if you had a double bond, then it kind of prevents us, right? Because the pi bond up there is preventing us from actually making that rotation. But here, even if it's not a like super basic 2 orbital like thing, we can still rotate it, even though there's like a bunch of stuff going on here. So yeah, that's about it. That's my explanation I guess, of orbitals using balloons. Hopefully, I interpreted the instructions correctly. I don't think I did, but I did the best I could. I made like 2 different molecules. I'm kind of happy about that. Yeah, thank you for watching. See you. Bye bye.